Hello everyone, welcome to VLSI Toolbox. Today I will be talking about analog circuit sizing with the help of soft computing algorithm. That is, we can get our optimized circuit design parameters using this technique within a short span of time. So let's check it out how it works. So before going to the next slide, let's know why this approach is followed. As you can see, the two approach shown in the slide. First one is the traditional method where lots of teamwork and hand calculation is required, which requires lots of time to achieve the task. Whereas in the optimization based approach or soft computing based approach, the optimization kernel will do the hand calculation part and it will minimize the human error and also time required. So with the short span of time we can get the result and we can use the result in our circuit simulator. So this is the workflow, and prerequisites for soft computing technique are target specification ranges. We have to set the target specification range and we have to choose one algorithm such as genetic algorithm, swarm optimization technique, and a objective function. That is the target specification can be obtained using some equation based on the circuit. So you can set that equations and other related things in a function called objective function, and you can set a target to minimize whether you are willing to minimize the area, whether you are willing to minimize the noise, whether you are willing to minimize other things, other parameters, or maximize other parameters as your wish. You can set in the objective function. And the tools required to use this technique are MATLAB for running the algorithm and get the output from MATLAB, and for verifying the MATLAB output you can use simulator like Cadence, Spice, any tools you can use. And for this demonstration we are using a human behavior particle swarm optimization algorithm. Regarding the algorithm, you can contact us if you want to know much, and check the publication link mentioned in the description. So let's go to the demo and see how it works. So this is the MATLAB code for a human behavior particle swarm optimization for analog circuit sizing. These are the initializations. I have used 100 iteration. You can use more. But step means the number of iteration, how much iteration you require, and this is the dimension, what are the problems dimension, actually what are the parameters. So these are the dimension a1 to a7, 7 dimensions I have put, and these are the ranges. So these are slew rate range 10 to 20 volt per microsecond. This is the load capacitance 5 to 10, and this is the gain range 70 dB to 100 dB gain, and this is the UGB range 3 megahertz to 90 megahertz, and this is the VIC range, mean common mode voltage range, minimum and maximum range, and these are the power consumption range. So based on this all the position metrics and other things will be formed, and corresponding we require one objective function. So in corresponding with objective function it will be called, and this objective function will calculate the design equations based on the input, and it will give the area information. So our main objective is to minimize the area, so we are giving the area information to the algorithm based on the minimum area and the design constant. It will give the values of W by L ratio of the op amp as well as other parameters. So these are the constants used during the calculation. These are the process parameters, and in this optimization we have kept the length of the transistor fixed to 2 micrometer. So all the lengths of the transistor are written here as 2 micrometer. So all the length is fixed, and these are the threshold voltages and other process parameters you can see, and these equations are taken from the Alan Hallberg books. You can go through it and take the reference from there. So let's run the algorithm and see the values what it's giving. So run, Now iteration is going on, and the area versus iteration curve is plotting. You can see here. So up to 100 iteration it will go. You can increase the iteration number based on your complexity. So it's finished. Now let's check the values. So for checking the values, let's paste the global variable that I have set already. So it's populated. Now you can see W1, W2, all values are here. 4 macro, 3, 4 same, and 5 is 2 macro, 8 is same. W6 is 16.85 macro, and W7 is 4.2 macro. And I require another values, the tail current 3 macro, 30 macro, 30 macro. And you can see also other parameter. If you want to see power consumption parameter, also their power distribution is something 35 macro watt, 335 macro watt. So in this way we can get all the values. Now these values will be given to the cadence, and we will try to simulate it and find whether it is matching or not, or whether it is within the range or not. So let's go to the cadence now and put these values and see the result. So now you can see here, this is the cadence schematic design, and these are the parameters that we have obtained it from the algorithm, and these are my specification. You can verify it from MATLAB itself. So you can see here all the parameters are written from this variable values, and in the objective function you can also verify the maximum 1.8 volt and minus 1.8 volt. So you can also verify it. I have just designed this circuit power supply 1.8 volt to minus 1.8 volt. So in this way I have designed, and let's do AC analysis. So for that, go to ADL, and I have just set the AC analysis test. So let's check the settings. AC 1 to 100 points per decade. So using these settings I am just going to simulate, and this is the common mode voltage, AC magnitude voltage 0 for differential gain simulation. This will be used for CMRR simulation, and these are the common mode voltage. So let's run it. Result, red plot, gain and phase, V out by V in. So these are the gain and phase plot. You can check the value 74.81 dB. So we have set the more than 70 dB gain. So 74.80 gain is coming. So it's meeting the specification. You can check the UGB point by pressing a horizontal marker, by pressing H for horizontal marker, and set it to 0 dB. So 5.5 megahertz. So UGB is greater than 4, so it's maintaining the spec. Also in the MATLAB you can also verify the ranges that we have set in the for UGB is 3 to 90, quite a large range, and within this range it is coming. So next you can get other information also, phase margin, gain margin. So from 0 dB, if you can press V for vertical marker and check the degree available, and then subtract it from minus 180 degree. So phase margin is not so good. You can also optimize it afterwards by tuning the compensation capacitance and load capacitance or other W/L ratio of output resistors. So you can also set it to these values for checking the phase margin. For checking the phase margin or phase crossover frequency, you can give here minus 180. Now you put one vertical marker, also here you can put one horizontal marker. So this is the phase crossover frequency and this is the gain crossover frequency. So this gap is the gain margin and this gap is the phase margin. So you can also enlarge it because it is not so good phase margin, so you can tune it afterwards. So this is the observation from this curve. So let's now do the CMRR analysis, common mode rejection ratio. For that you have to do parametric analysis. Tools parametric analysis 0 to 1 volt, because the input we have given to the positive terminal as 1 volt AC magnitude. So in the parametric analysis 0 to 1 we will do two graphs will be required. One is for differential gain, another is for common mode gain. So let's run it. Result head plot, gain in phase, P out by B in. So you can see here one is differential AD and this is AC, common mode gain. So let's delete the phase. Let's take it to the calculator. Now copy it by selecting minus. Now give to 1. So now plot it. So here you can get 77 dB CMRR. So this is the CMRR plot. In this way you can do CMRR analysis. Other analysis there, PSRR plus and PSRR minus, which I will be showing in the next part of the video. So hope I have given you some valuable information in this video, and I have tried to show you a process of analog circuit sizing using soft computing, and in my next video I will show you other analysis. So stay tuned and subscribe my channel. Thank you.